Hey guys, welcome to the Hannah and Slimey channel. We're going to be teaching you Calculus 101 today. Hannah, take it away.
Alright, first we're going to start with the basis of all of calculus, limits. Limits describe how a function behaves near a point instead of at that point. Limits allow us to describe how the output of a function behaves as the input approaches a particular value. Limit notation looks like this. The limit of f of x as x approaches c equals L. This means that the values of f of x of the function f approaches or equals L as the values of x approach c. This simple yet powerful idea is the basis of all of calculus. Let's take a look at this graph to better understand what a limit is. We can see here that as the x values approach 3, the y values approach 5. However, this is not to be confused with the value of x equals 3. If the value of x equals 3 is undefined, it would look like this. The limit does still exist and is still equal to 5 even though there is no value. There are 4 main ways to solve a limit: substitution, rationalizing, factoring, and graphing. We just used the graphing method to solve the example. This method is most useful for more complex graphs and with distinct behaviors. Substitution is the most straightforward method. All you have to do is plug the limit right into the function and there you go. Rationalizing involves manipulating a function and creating a form that allows for substitution to occur. Factoring is a form of rationalization in that it breaks down the equation into simpler parts before substitution. We can use limits to find an average rate of change, which is the amount of change divided by the time it takes. The notation for average rate of change looks like this. F of b minus f of a over b minus a. A. The book says that this concept can be applied in real life, but in reality it probably can't. We can even use limits to find the slope. The slope of a curve y equals f of x at the point a, f of a is the number m okay. M equals limit as h approaches 0 of f of a plus h minus f of a all over h. This idea is essential to all of calculus and cannot be forgotten. It is what allows us to find derivatives and tangent lines and all that fun stuff we'll get to next. Next is derivatives. A derivative shows an instantaneous rate of change or slope. We previously showed the formal definition, but hey, we'll remind you. We can define the slope of a curve y equals f of x at the point where x equals a to be m equals the limit as h approaches 0 of f of a plus h minus f of a over h. This value is the derivative of the function with respect to the variable x and is known as f prime, which looks like this. Aside from using limits and the formal definition, there are many ways to solve for a derivative of a function. First, it is important to know that the derivative of a constant is 0 and the derivative of x is 1. The next rule is a first step toward a rule for differentiating any polynomial. The power rule states that if n is a positive integer, then the derivative of x to the n equals nx to the n minus 1. For example, the derivative of x squared would be 2x. The derivative of x cubed would be 3x squared. The rule works the same way for negative exponents. Take y equals x to the negative third, for example. Y prime would equal negative 3x to the negative fourth. The same goes for fractional exponents as well. 2x to the 1/3 would be 2/3 x to the negative 2/3. This is my favorite rule. Next is the product rule, which allows us to find the derivative of two functions multiplied together. Let's take y equals f of x times g of x, for example. Y prime would be equal to f prime of x, g of x, plus f of x times g prime of x, which can also be denoted as y prime equals u prime v plus u v prime. Its counterpart is the quotient rule, which lets us find the derivative of two functions that are divided. For the quotient rule, y prime equals f prime of x, g of x, minus f of x times g prime of x, all over, all over g of x squared, which can simply be named as u prime v minus v prime u all over v squared. Next is the chain rule, which allows us to find the derivative of a composition of a function or a function inside of a function. In order to differentiate, we have to multiply the derivative of the outside by the derivative of the inside. For example, take y equals sine squared x. First, we can rewrite this as y equals sine of x squared to make it a little bit easier. Then we'll take the derivative of the outside by moving the 2 to the front and subtracting 1 from the exponent. Which will leave us with 2 sine x. Because we still have part of the function that we have not yet derived, we must differentiate this portion and multiply it by 2 sine x. So then we get 2 sine x times cosine x, which is the derivative of sine, which will finally be written as 2 sine x cosine x. Speaking of trig functions, we must know the derivative of each of the following functions. And there are a few other miscellaneous functions we should be able to derive. In addition, we must also know the inverse trig functions and their derivatives.
So now that you guys are experts on derivatives, we're going to start applying your knowledge. So, I'm only going to tell you the important stuff. So we're going to start with extreme values of functions. Okay, so we're going to start with the local max and minimum. So, say you were given a graph like this. So, the local max is the height of the function at which a is greater than or equal to the height anywhere else in that interval. And the local min is the height of the function at a is less than or equal to the height anywhere else in that interval. So what that means is it's not the highest point, but it's not the lowest point. So the local maximum, well, there could be more than one, but this is the local max. And this is the local min. And you're probably wondering, what is this big bump doing? We call that the absolute maximum. So there's only one absolute max and absolute min. So this will be the absolute max. And then down here somewhere will be the absolute min. So next, I'll be teaching you about the mean value theorem. The mean value theorem states that between the continuous interval AB, there must exist a point C where the tangent at f of C is equal to the slope of the interval. In other words, it means instantaneous rate of change equals average rate of change over a closed interval. So, this would be the equation. So, to do an example, we're going to do, say you were given the function f of x equals 3x minus x squared. So, using this equation, oh, and you're given the interval. We're going to solve this. So, you'd find the derivative of this first. So, 3 minus 2x. You set it equal to f of b. So, f of b would end up being 0. F of a would end up being 2. And then b minus a. So, 3 minus 2. You end up getting 3 minus 2x equals negative 2. Then, it's simple algebra. Negative 2x equals negative 5. X equal 5 over 2. And that's the mean value theorem. That's not all. We got critical points. A critical point is a point in the interior of the domain of a function f at which f prime equals 0 or f prime does not exist. So say you were given the function 4x squared minus 16. So first, you would find the derivative, which would be 8x minus 16. Then you would set that equal to 0. You'd factor, so this is x minus 2. Then you get x equal 2, and that's your critical point. So now I'm going to talk about the graphs of f prime, and f double prime. So, as you can see from this picture, the function y equals x cubed rises as x increases, but the portion defined on the intervals negative infinity and 0 and 0 infinity turn in different ways. Looking at tangents, we can scan from left to right to see that the slope y prime of the curve decreases on the interval negative infinity 0. This decreases. And then increases on the interval 0 to infinity. Here, increases. The curve y equals x cubed is concave down on negative infinity 0 and concave up on 0 infinity. The curve lies below the tangents where it is concave down and above the tangents where it is concave up. The next topic we will be talking about is optimization. Optimization problems in calculus often involve the determination of the optimal value of a quantity. For instance, we might want to know the biggest area that a piece of rope could be tied around, or how high a ball could go before it falls back to the ground. Or at which point of a loop does a roller coaster run the slowest. Very often, the optimization must be done with certain constraints. In the case of the rope, we're limited by its length. These constraints are usually very helpful to solve optimization problems. Optimal values are often either the maximum or the minimum values of a certain function. There are actually 6 easy steps to do this difficult concept. Step 1, determine the function that you need to optimize. Step 2, identify the constraints to the optimization problem. Step 3, express that function in terms of a single variable upon which it depends using algebra. Step 4, calculate the derivative of the function with respect to a variable. Step 5, set the function to 0 and compute the corresponding variable's value. Step 6, Use the value from step 5 to calculate the corresponding optimal value. Yeah. Next, I will be talking to you guys about related rates. Related rate problems involve finding a rate at which a quality changes by relating that quantity to other quantities whose rates of change are known. The rate of change is usually with aspect to time. Next, we will talk about the point of inflection. The point of inflection is where the graph of a function has a tangent line and where the concavity changes. So it can either be from positive to negative or negative to positive. In this function that we have here, the point of inflection is right on 0, 0. Woo! Next we will be talking about indefinite integrals. So use substitution. When finding antiderivatives, we are basically doing reverse chain rule. This concept is not always straightforward, so one useful method is use substitution, which is chain rule in reverse. So say we are asked to find integral cosine 7x plus 5. First, we will start by assigning u to the term 7x plus 5. Then we find what the derivative of 7x plus 5 and we make that du. Then we solve for dx, which is, let's say dx. So you just divide and get 1 over 7 dx, or du. Then we are ready to substitute back into the integral. By using the constant multiple rule, we get 1, 7 cosine of. Once we find the integral of that function, we get 1/7 sine u plus c. Then all you have to do is substitute 7x plus 5 back in for u. And then your answer is 1/7 sine 7x plus 5 plus c. That's your answer. Next, we will be talking about definite integrals, specifically fundamental theorem of calculus. The fundamental theorem comes in two parts. The first part says that the definite integral of a continuous function is differentiable function of its upper limit of integration. Moreover, it tells us what that derivative is. The second part of the theorem tells us that the definite integral of a continuous function from a to b can be found from any one of the function's antiderivatives f as a number, f of b minus f of a. The integral of a to b, f of x dx equals f of b minus f of a. That might seem confusing, but here's an example to clear things up. So, say you are given d over d of x 0 to x. So 1 over 1 plus t squared dt. So, solution is f of t equals 1 over 1 plus t squared. So the answer is just 1 over 1 plus x squared. Simple.
Now that we have discussed integration, we can take it to the next level and apply it to graphs. This will allow us to find the area between two curves, volume by cross-section, volume of a solid with revolutions, and the length of curves. We will start with finding the area between two curves. Take these two functions for example. Y equals 2 minus x squared and y equals negative x. Consider a vertical strip on the line x equals 1. We can say that the length of this strip is y1 minus y2, or 2 minus minus x squared minus negative x. So then we can infer that length times width is equal to 2 minus x squared plus x. Dx. To find area, we then must integrate this function. However, we cannot integrate without bounds, so we first have to find the intersection points of the two functions. We can do this graphically or by setting the two equations equal to each other and then solving for x. In this example, the bounds are x equals 2 and x equals negative 1. So we will integrate from negative 1 to 2. Our integral should look like this. After integrating, we find that the area between these two curves is equal to 27 over 6. In general, we should know that the area between two curves is the integral of upper minus lower. In order to find volumes, we must have a solid understanding of solving for area, and we know that we are probably so confusing, so please feel free to rewind the video now. The first method of finding volume of a solid is by cross-sections. We can identify these types of problems by looking for the word cross-sections followed by a shape. We will cover the four most common shapes used to find volume. First, we must establish that S is equal to upper minus lower, which we just discovered was area. Another important thing to remember from the area section is that the bounds are simply the intersections of two functions. Okay, so first we have squares. To find the area whose cross sections are equal to squares, we use the formula s squared. So if we use the example from the previous section, the integral to find volume with cross sections of squares would look like this. S is equal to 2 minus x squared plus x. Then, because it is a square, all we have to do is square the function. The other shapes work similarly, except their formulas differ. These must be memorized as well. First, we have squares, which we just discussed. Their cross-section is equal to s squared. Then we have semicircles, which equal pi over 8 s squared. We also have equilateral triangles, which are equal to the square root of 3 over 4 s squared. And lastly, we have isosceles triangles, which are equal to 1/2 s squared, where s is area. Now for the good stuff. Volume by revolutions and rotations. The volume of a solid that is rotated around an axis or a line is the integral of the cross-sectional area. We can break this down into disks and washers. The simplest solid of revolution is called a disk, which is formed by revolving a shape about an axis adjacent to one side of the shape. To find the volume of a disk, we use the formula V equals pi times the integral from c to d of r x squared dx. Let's do an example to better understand. We are going to find the volume of the solid formed by revolving the region bounded by the graph of f of x equals the square root of sine x and the x-axis about the x-axis. If we were to sketch this graph, we could tell that the radius of the solid is the square root of the sine of x. So r equals square root sine x. Thus, the volume of revolution is v equals pi times the integral from 0 to pi of the square root of sine x squared dx, which when we solve comes out to be 2 pi. The disk method can be extended to cover solids of revolution with holes by replacing the representative disk with a representative washer. The washer is formed by revolving a shape about an axis. R is the outer radius, and little r is the inner radius. And the formula for washers is as follows. V equals the integral from a to b of pi big R squared minus pi little r squared dx. Always forget that. The integral involving the inner radius represents the volume of the whole and is subtracted from the integral involving the outer radius. In order to solve for the volume using the washer method, we must first establish these inner and outer radii. From there, we can easily integrate with respect to x or y. Last, but certainly not least, we will find the length of curves. We use the following formula. Arc length
The positive length
equals the integral from a to b of the square root of 1 plus dy dx squared dx. For example, if we wanted to find the arc length of the curve y equals x squared on the interval 0 to 4, we must establish that the bounds of integration are 0 to 4 and that dy dx is equal to 2x. So our integral would look like this. From 0 to 4, and square root of 1 plus 2x squared dx. And then you just plug it in your calculator and you get your answer. Easy as pie. Thanks for watching our video. Sorry if it wasn't very helpful.
We don't get it either.